situation we have is somebody standing on a large wheel, constrained about an axis through the center, perpendicular to the wheel. Wheel has a fairly large mass. The person standing here is subject to force of gravity acting downward. Now, if that person is considered to be part of the wheel system, you don't have to worry about the normal force on the person or any of the forces exerted between the wheel and the person, except for the gravitational force on the person. So, the person is on a wheel of radius 3.5 meters, and what was said is that the vector indicating the force of gravity located at the point of contact from the person in the wheel, if extended, passes within 1.5 meters of the axis, meaning that this distance here is 1.5 meters. The distance of a line from a point is measured at the point where your line, it's measured from a point on the line, which, when extended in the direction perpendicular to the line, goes through the point. Okay, and I didn't say that well, but that's something everybody should know. Okay, so this is 1.5 meters. Now, from that, we want to conclude several things. First of all, what's the angle as measured from the positive x-axis in the counterclockwise direction? By the circular definition, which I scribbled down here, and I'll reference at the end in the last video I do on this situation. We determined that r cosine theta is your negative 1.5 meters, so that r being the radius of the circle, 3.5 meters, times cosine theta is negative 1.5 meters. We can easily solve for cosine theta. But we can easily determine theta from the cosine. Now, if we solve just taking the arc cosine of negative 1.5 over 3.5, we get something like about 2 radians. Okay, well, that would be the angle up here. And we should understand, and we should know from pre-calculus, second semester pre-calculus or trig, that there are 2 solutions to this equation. One, both corresponding to points that project down to here or up to here. So there's one solution corresponding to this angle here that would have a radial line from here out to here, and that's a solution you're going to get if you punch the arc cosine of negative 1.5 over 3.5 into your calculator. And that's about 2 radians, and of course that's consistent with our picture. A radian's roughly 60 degrees. It looks like that's about 120 degrees. So roughly 2 radians is a perfectly reasonable solution. Now, what solution down here corresponds to this? There are 2 ways to look at it. The angle between here and here is theta pi minus the approximately 2 radians we get here. And if we add that then to pi, we get this, okay? Or if you want to think about it in degrees, which is more intuitive at this point, but we really want to think in terms of radians in this situation. Still, if this is about 120 degrees, then this angle's about 60 degrees, meaning this angle's about 60 degrees. And from 180 degrees down 60 degrees gives about 240 degrees. So we get like 120 degrees and 240 degrees. Now this angle then would coincidentally be about double this angle. That's not a general case. If it was 110 degrees here, you wouldn't have 220 degrees down here, you'd have 250 degrees. So the angle doesn't automatically double. 120 degrees coincidentally would. The other way to determine what this angle is if we take the angle around to here and subtract it from 360 degrees, or from 2 pi radians, we're going to get this angle. So this angle, this solution to the equation cosine theta equals negative 1.5 over 3.5, looks to be about 4 radians, and if we run it through our calculator, we find that it's about 4.27 radians. Notice that I put the radians on the 4 here. I didn't put the radians here. I didn't put any unit on this because radian is the default unit of angle measure. If I put down an angle without any indication of the unit, it's automatically radians. And of course that means if your angle's in degrees, you'd better put the degrees on it. Okay, radians is optional. And the parentheses here just means that was from a calculator. You don't have any good way of calculating. So I mean, it can be done, but nobody's right mind would do it except as an exercise to understand the approximation technique. Okay, so anyhow, we've determined that a person standing here is going to, that the radial line from the center down to here is going to be at an angle of 4.27 radians as measured counterclockwise from the positive x-axis. Now, we ask if theta changes by, I wrote 0.1 radian, and this should have been 0.01. Very tiny change in the angle, 0.01 radian. Then, by how much does the vertical position of this mass, this person, change? Okay. Well, to answer that question, we kind of digress a little bit, okay? What we do is we sketch the gravitational, because, okay, it should be clear that on this problem we're asking about the change in potential energy, not how far the person descends. Okay, change in the gravitational potential energy. Now, we digressed a little bit to the idea that the change in potential energy is equal and opposite to the work done by the conservative force, and I'll talk about that a little bit, but I'll just say gravity is your conservative force here. So we want the work done by gravity, and then our change in potential energy will be equal and opposite to that. Okay, well, the work done by gravity, as we know from having used projections in this type of situation, is what we get when we either project our displacement vector on our gravitational force vector and multiply the projection times the vector onto which we projected, or do the same thing by projecting the gravitational force onto the displacement vector and multiplying that projection by the displacement. So in order to answer the question of the potential energy change, we just want to use this picture, gravitational force displacement vector, and for reasons it'll become apparent, we want to probably project the displacement onto the gravitational force. In this situation, there are situations like on an incline where you want to project the gravitation onto the displacement. You get the same answer either way, but conceptually it comes out a little bit differently. So we want to understand this diagram, we understand this little triangle here, and we want to get some idea of how we calculate the change in potential energy in this situation, given this change in angle and this angle.